Uh, okay, good morning, and so for last few lectures I was in America, so I couldn't do the physical offline classes. So I uploaded a few videos for the VLA models and the advanced algorithm like DPU and GRPU, and today we'd like to incorporate them to improve VLA models with reinforcement learning. And these are two topics that we will cover. As this is a very recent topic, we'd like to just very briefly cover them. We are not going to see some details of them. And so first one is why and how to add RL to VLA, and the second one is our fine-tuning method for VLA. So this lecture combines the two ideas from previous classes to close the course. And so from the VLA lecture, VLA models are scaled-up imitation. They copy demonstrations, so they cannot exceed the demonstrator. As I said, VLA models just with a huge amount of pre-training and teleoperation data, we just train VLA models with the behavior cloning, just simply supervised training. But the drawback is that they cannot discover better strategies, and they have no way to recover from their own mistakes. That is the limitation of VLA models. And from DPU and GRPU lecture, we just covered how DPU and GRPU are used for language model, not for robotics, but DPU and GRPU are very useful. So we now have tools to improve a model from reward after training. After supervised training, we now have some tools like a DPU and GRPU to improve a model from reward and preference, not just demonstrations. We've covered DPU and GRPU for language models, and today we will try to incorporate DPU and GRPU for VLA models. The natural next step is use reinforcement learning to fine-tune a VLA, so it improves beyond these demonstrations. And recent VLA works as a third stage on top of pre-training and imitation. The first one is almost like a language model that I covered in previous time. Pre-trained with the vision language, this just becomes VLM model. It gives us the internet knowledge about the world, not about specific robotics application, but about just understanding what is happening from the observation. And SFT, supervised fine-tuning, let's see we have some reasonable amount of teleoperation data set, and then we can do supervised fine-tuning by imitating demonstrations, copying expert, and then so far that was the typical VLA. We've covered them in the previous lecture, and then today we will incorporate RL to improve the VLA model by reward to surpass the expert. That is today's topic. The first two stages are imitation. As I said, they can only reach the quality of demonstrations. The RL stage is where the model can finally improve beyond them, which is the focus of this lecture. So what does RL add to a VLA? So reinforcement learning optimizes the policy directly through trial and error guided by the reward. And this gives a VLA four things that pure imitation cannot. The first one is surpassing demonstrations. It can find strategies better than any in the demonstration set. As I said, the behavior cloning is just to copying the expert, but we sometimes want to exceed, doing better than demonstrations. And corrective behavior, it learns to recover from mistake by experiencing their consequences. So the VLA models, the robot control is basically auto-regressive one, so that the output of the current iteration becomes input of next iteration, so that anyway, if there is something bad happened, then the agent should recover from the mistakes. So that corrective behavior is actually very important for such kind of auto-regressive system. And by incorporating reinforcement learning, it learns to recover from mistakes. Because RL, naturally it does some explorations with the environment. And generalization, RL-tuned policies often held out of distribution situations better than supervised fine-tuning. That is also true, right? Because the RL-tuned policies do some random interaction with the environment and find some out of distribution cases, so that it could generalize better than some model simply trained with the SFT. And long horizon skill, reward over a whole task helps chain many steps toward the goal. In short, RL turns a passive imitator into an agent that actively improves at the task. And let's see why and how to add RL to VLA models. A concrete example why copying is not enough is described below. Imagine a VLA trained by imitation to pour water into a cup. During the real attempt, it tilts slightly too far, and the cup starts to slide, a situation no demonstration ever showed. Because, although we cover a huge amount of demonstrations, we cannot cover all such kind of cases for all tasks, right? So there can be always some unseen cases. And that is the example. Let's say we are pour some water into a cup and there is something bad happens. Because it only learned to copy demonstrations, it has no response to this new state and fails. That is actually, it can be partially addressed with the huge amount of pre-training and data set, but that's essentially just a covariate shift, right? In behavior cloning, we learn covariate shift. A demonstrator never made this exact mistake, so the data contains no recovery to imitate. With RL, the robot can try, fail, feel low reward, and gradually learn a corrective motion on its own. So this is the core reason we added reinforcement learning on top of imitation-trained VLA. And why RL can beat imitation? Imitation copies the average behavior in the data, mistakes and all, and never questions whether it is optimal. RL instead asks which action actually lead to high reward and reinforces those. And because it learns from outcomes, RL can prioritize the few critical decisions that determine success. There is strong evidence that RF fine-tuning gives much better out-of-distribution performance than supervised fine-tuning alone. And we actually saw this in the language model, right? In the previous time for the GRPU and DPU. We find that reinforcement learning is, post-training with reinforcement learning is very helpful to improve the language models. That is actually, at this moment used in the language models. But applying R to large VLA brings unique challenges, which we go through one by one. The first challenge is, where does the reward come from? Unlike a game with a built-in score, just a video game, we have a built-in score, pre-designed scores. A robot task has no obvious reward signal. Common choices in VLA work: sparse success reward. 1 if the task is completed, 0 otherwise. Simple but hard to learn from, just a binary reward. Very favorable reward, automatically checkable outcomes, like whether the object was grasped or placed correctly. This is the, I guess, most widely used case at this moment. But still, we need to design reward by ourselves, which could be suboptimal, and we cannot. In some cases, calculating some reward is infeasible. The third one is kind of promising direction at this moment. Word model reward. The learn model predicts outcomes and scores them, avoiding real robot rollouts. Word model is, it becomes a popular topic, but it is actually a little bit ambiguous. What is exactly word model? Each people define word model in different ways, but maybe a common definition among people would be just like a diffusion planning. We cover diffusion planning, right? Diffusion planning is denoising state and action together, or just state. Doing some diffusion, generative modeling, a trajectory of state and action, or doing generative modeling on state, and then, so that if we do something, if we do some actions, then in reality, actually, we need to physically control robots to get some observations, right? When we do some action, then we let robot do something, and then we get observation. Then we can compute rollout, but definitely that is not a very good way, because robot can be broken during rollout, and that can be a little bit slow. And there are many hardware issues, so that word model is trying to do simulation to simulate such kind of robot rollout in a more realistic way than current physics simulation like Isaac sim. In our final project, we are doing simulation-based rollout with the Isaac sim, but Isaac sim is good for physics, but actually it has very limited capability for photo-based rendering or lighting. There are many, some visual stuff are actually very limited to mainly focusing on physics, so that it cannot cover like a non-rigid deformation like a hair or water or fire. There are many things that are not incorporated in isocene. So that, but the world model, it tries to like doing generative model for state or state action on from the videos, so that it can be used for more realistic rollouts instead of physics-based simulator. Also avoiding real robot rollout, that is the world model. We are not going to cover details of world model because that is out of scope, but that is the one promising way at this moment people trying to do for robots. Anyway, but the verifiable reward is the most valuable option at this moment. And reward design is the central practical difficulty. A bad reward leads the policy to game it instead of doing the task. And anyway, that is the first challenge. And second challenge is the action representation matters. RL with policy gradient, this probability, the policy assigned to an action, we need this one, right? For the policy gradient, we need this one. For example, if we do PPO, we always use this one, right? For token-based VLAs, like discrete VLAs, right? Discrete representation VLAs. For example, RT2 and Open VLA. Actions are discrete tokens, so this probability is easy to compute. But we know we perform softmax on the discrete tokens, so that the output of softmax directly becomes likelihood for this one. So that it is very easy to compute such kind of likelihood for discrete token-based VLA models. For most VLA plus RM methods so far target exactly this auto-regressing model for that reason. So this token-based or discrete token-based VLA models like RT2 Open VLA, as I said, it is discrete token-based one. There's no continuous stuff, so that it is easy to get likelihood because we do softmax on the output token, and then just using numbers from softmax becomes a likelihood. That makes so getting this kind of likelihood easier. But the problem is that for this kind of discrete token-based VLA models, as I said, suffer from the quantization errors. Like it cannot do some high frequency detailed manipulations because it's based on discrete tokens. That is a good point about pros and cons of this kind of token-based VLA models. But getting probability becomes much easier for this kind of discrete token-based VLA models, and that is the reason why most recent VLA plus RM methods so far target this kind of VLA models, because we can easily get likelihood. On the other side, we have flow or diffusion-based VLAs like Pi0. These are continuous VLA models, right? Continuous VLA models, actions are generated by iteratively denoising, so the action's likelihood is intractable. We cannot easily get this kind of likelihood for flow or diffusion-based VLAs, so that is the reason why recent VLA plus RM method so far targets exactly this kind of discrete token-based VLA models instead of continuous flow-based or diffusion-based VLA models. Recent work such as PyRL developed special technique to apply online RL to these flow-based models. So recent PyRL tried to incorporate RL to this kind of flow or diffusion-based VLA models. Still, that is still work in progress. And the third challenge is online versus offline reinforcement learning. Online reinforcement learning policy interact with the environment that is online. Offline means learn from fixed data set. Learn from its own new experience online. These are simulator of real robots. It's costly, interview gap, safety concerns. But one good point is that learn from its own experience. Offline RL, no environment interaction needed, safer and cheaper to run, but vulnerable to distribution shift. So that we can, recent method try to incorporate them. Online RL can surpass the data, but it's expensive. Offline RL is safe but limited. Many methods blend the two. The alignment tools from last lecture transfer directly to VLAs. GRPO fits naturally. Sample several action sequences for a task, score them, and reinforce the better than average ones without critic network, without value network. The group relative advantage needs no critic, which is attractive for large VLAs, where value network is costly. I mean, in your final project, your policy and value network might consist of several fully connected layers. That is not very expensive. But large VLA models, they often have large-scale VLM models, right? Pre-trained VLM models. So that having two VLAs for action, for policy and value network, that is really costly. But GRPO, as I introduced, it does not require a value network. So that GRPO is actually very attractive for doing RL, incorporating RL to VLA, because we do not need to use a separate value network. And DPO style training fits when we have preferences over robot behaviors. This trajectory is better than that one. So the same recipe that align language model now improves the robot policy. That is the some philosophy of today's topic. We saw some advancement in language model with GRPO and DPO, and we'd like to incorporate them in the robot policies as well. So concretely, a sample a group of action sequences for the same observation, score each with the task reward, and standardized within the group. It's just a GRPO, right? Just a GRPO. Then update the VLA policy to raise the probability of high advanced action sequences, exactly the GRPO idea applied to robot actions. The reward RI now measure the task success instead of human preference, but optimization is the same. Right? So mathematically, it's almost the same as the language model, but data, some of the tasks are a little bit different. But the philosophy is almost the same. Let's see our fine-tuning method for VLA. We will try to just quickly see some examples how we can incorporate RF fine-tuning for VLA models. And there are three families of VLA RL method: online RL, offline RL, and test time RL. Online RL improves the policy by interacting with simulator of robot and updating. But offline RL squeezes a better policy out of fixed data set without new interaction. And test time RL does not retrain. From pre-trained policy, we just sample several actions and use a value estimate to pick the best one to execute. We sample a few representative methods, kept light to see the landscape. The first one, scaling and stabilizing online RL. You do not have to memorize all the details of this method's name and the example. Just to see how each paper tries to address some problems of each RL fine-tuning scenarios. Simple VLA RL applies a GRPO style approach to scale up VLA training with RL. It shows the RL lift performance even when only a few demonstrations are available, reducing reliance on huge demo sets. And IRE, I might be iterative. IRE VLA, alternating between RL exploration and supervised fine-tuning. Iterating two stabilizes training of large VLA, which can be fragile under pure online RL. The theme is to make online RL practical and stable at VLA scale. If you're interested in, you can visit this paper, but you do not have to memorize all this name and the contents of this paper. And the second method is new objective and flow models. RIPT VLA, RIPT VLA, interactive post-training using a simple reinforced style objective. RLOO is like a reinforce, leave, one, out. In short, RLOO. Reinforce style objective, leave, one out, baseline. That is in short, RLOO. It refines an already trained VLA with lightweight online feedback and PyRL. We covered this very briefly in the last slide, right? Brings online R to flow-based VLA like the Pi0 family. It tackles the interactive action likelihood problem that block RF for diffusion and flow models, right? We covered that this kind of action likelihood is necessary for doing the PPO style RL, but this kind of flow or diffusion-based policies, VLA models, As they do diffusion, we cannot get likelihood. It is intractable to get likelihood. The pi-RL do some approximations to get likelihood for diffusion of flow-based models so that we can incorporate RL to such kind of diffusion of flow-based models. The theme is extend RL beyond token-based VLA, like pi-RL, and explore simple objectives. And the third method is learning from real experience. Pi star 0.6 from physical intelligence is a recent VLA explicitly designed to learn from its own experience. Rather than only imitating demonstrations, it improves by practicing tasks and then using outcomes as a learning signal. This points toward the long-term goal. Robot can keep getting better, and the more they operate like a person practicing a skill, theme is close the loop, so deployment itself becomes a source of improvement. A lightweight option is test time RL. It's very practical actually. I mean, for any cases, if we need to train some large models, we should be very careful. We need to preserve some prior knowledge of pre-training while incorporating new knowledge from field data. That is not very easy. And of course, training requires much more computation than test time computation, so that test time RL, along with the test time, there are many test time training these days actually. Test time RL, test time do something in video generation, test time do something in blah blah are very popular in these days because they're very practical. We can preserve the prior knowledge of pre-trained models while we do something better in the test time. Not every method retrains the model. Test time RL improves behavior at the moment of acting. The idea is at each step, sample several candidate actions from VLA, then use a value estimate to rank them. And execute only the top ranked actions so better choice is made without changing the model's weight. This is cheap and safe because there is no training loop, but it cannot teach the model genuinely new skills. It is a practical middle ground when full RL fine-tuning is too costly or risky. So, it is like it is these days called like a steering. It is not only for RL or robot stuff, but also for video generative models. Steer is like adjusting some direction when we driving. We have handle when we drive a car, right? So that we can change the handle orientation, so that we can change the direction of the car moving. That is steering, meaning of steering. When we do some sampling in diffusion models, we iteratively sample some data from the pre-trained, the generative distributions. Then we can do something during the sampling. The easiest example would be just classifier-free guidance. Roughly saying, CFG could be kind of example of steering, very roughly saying, because we do something during the inference to encourage our sample data satisfy some constraint during the inference. We steer our sampling process. So the CFG could be one example of steering. For the test time RL, we actually have value network, right? We have a value network. Or some reward if you use the GRPO. Anyway, we have some way to, let's say we have some way to evaluate our sampled action and state is good or not. Then for every iteration, we can evaluate sampled action and state, and then based on the evaluated sample and action, we can steer our sampling process to that direction, to the direction with high reward. If we keep doing that during the inference, iterative denoising of the generative diffusion model, then the final sampled action would be better than just sampling without some special technique like steering, right? That is the philosophy of test time RL and steering. As I said, this is also very recent and popular topic these days, not only for robot stuff, but also all kinds of generative models, especially video generative models. Because training video generative model is too costly, so that people try to incorporate some smart way to improve models in inference time without retraining one. And steering, test time RL is a good example of such kind of effort. Anyway, that is the test time RL. We use a value estimate For iterative sampling, iterative noising, we can evaluate our sample data based on our value estimation or reward computation, anything we can evaluate our currently sampled data, and then we can steer our sampling process to that direction with higher value or reward. That is the philosophy of steering or test time RL. And there are open challenges. So VLA plus RL is a promising but young with several hard open problems. Reward design, defining reward that capture true task success without being gameable. Right? It is also not very easy. How can we define reward? That actually is not very easy. In your final project, I guess your policy function might be very sensitive to reward function or reward weight. Such kind of sensitivity might not be applicable to this kind of huge system because VLA plus RL, your policies are just trained from scratch with RL, so it is naturally very unstable. But VLA plus RL, as I said, VLA, until some point, it is trained with the supervised training, so that it is much more stable than your policy functions. But still, when we're incorporating RL to pre-train VLA models, it becomes a little bit fragile, so that reward weight on which reward function you're going to introduce might affect training stability. So reward design is the one problem. And sim to real gap is also true. Policies trained in simulation often degrade on real hardware. If you just simply do IDOC-SIM, then your agent might suffer from severe sim to real gap because IDOC-SIM, as I said, cannot reflect all such kind of real-world physical properties and physical situations. So that there's a sim to real gap. Sim is simulator and real is real environment. And that is one of the reasons why these days people try to do world models, because world model, as I said, is more realistic simulator than current physics-based simulator. The world model, most of the world models just simply train with the real-world videos, right? So that it'll be much more realistic than the physics simulator like IDOC-SIM. So that if we use more realistic simulator, then of course we can reduce the sim to real gap, right? So that, and that is also one problem at this moment. Although people are working on world models, actually the quality of these days world models are not very good because it is not mature at all. So that there is also a problem. And cost and safety. Real world RL is expensive and can be unsafe during exploration. That is true because robot can broken and it can crush the human, and there can be many dangerous situations. Flow-based models. Applying RL to diffusion mode and flow VLAs is still being worked out. It is also a very popular topic. Flow is, I'm not sure you learned flow. Flow is a kind of advanced version of diffusion, DDPM. So the flow is kind of some good way for generative modeling these days, so that we can make our policies better with flow, especially for continuous VLA models. And incorporating such kind of flow for the diffusion is also an open research topic. These are exactly the kinds of problems where the RL foundations from this course apply. And let's see the whole course in one picture. Of course, there is a basic RL, like DQN, what we learned, police gradient, or PPO. These are just the basic RL. But these are, based on this basic RL, we can understand this one. This is the whole pipeline of robotic research these days. So that, as I said, the VLA models are trained with the imitation learning from scratch. Of course, we have pre-training. That is not the part of robotic. That is some computer vision and language stuff. Let's say we have a pre-trained VLA models, and then we can do SFT with the imitation learning, right? Like behavior cloning, Dagger, IRL, Gale, with imitation. Let's say we have a teleportation data or any data, any large-scale data, and then we can do imitation learning to train our VLA models, right? So that we have VLA models, scaled-up imitation. So far, it is kind of good, but it is not very enough because just a supervised training so that it might suffer from covariance shift, right? So in this exploration to make it generalize better the novel environment, and DPO and GRPO or PPO, anything, DPO, GRPO, or PPO can be used this direction. Online from preference reward, DPO and GRPO are mainly used in language models, but we can incorporate such kind of concept in the VLA models to encourage exploration, and then we can make it generalize better to novel environment. For this one, maybe, still we need to use DPO and GRPO are just basically RL algorithms, right? So we need some rollout. That means we need some simulator. So far people have used Isaac Sim, but maybe world model can be included in this direction, a better simulator than physics simulator like Isaac Sim. So making world model is also a good, important research direction to make robots better. And that is where computer vision, computer graphics, or such kind of visual computing meets this kind of robot research. Of course, there are many points where computer vision, computer graphics meets robot research, but this kind of thing is also an important topic where computer vision, computer graphics, and the diffusion models and robots meets at this point. How can we make better world model so that we can make a good simulator, a more realistic simulator than physics simulator like Isaac Sim. And once we have all such kind of stuff that we can do, VLA plus RL self-as demonstration, hopefully. But so far, very few people or nobody showed this one. But I guess this is some reasonable direction. The arc of the course is learn to copy experts, scale that up with foundation models, and use reinforced learning to go beyond them. Imitation taught the agent to copy, reinforced learning taught it to improve. So we can close the loop between imitation learning and RL algorithms, right? So let's summarize. VLA is a scatter imitation, so they need RL to improve beyond their demonstrations. The modern paradigm is pre-trained and supervised fine-tuning, then RL fine-tuning. The key challenges are reward design, action representation, and online versus offline reinforcement learning. GRPO and DPO from last lecture transfer directly, scope sample action sequences and reinforce the better ones. Recent method like this kind of VLA model show RL can make VLA surpass their demonstrations. And so that from the beginning of this course, we begin with the basic of reinforced learning and ended with the frontier of robot foundation models. The same core idea ran through everything, learn behavior from a signal, whether a reward or demonstration or preference, imitation, inverse RL, VLA model, DPO, GRPO, VLA plus RL, still all variation on that single theme. Thank you for a great semester, and okay, this